Yeah, thank you very much. And I would especially thank the organizers for setting up this very nice program and this workshop. So it's the third time I'm here during this program, and I really enjoyed my time. And I think I can also present one result which I worked out here. Well, unfortunately not yet published, but let's see. Okay, so so this is about compressive sensing, and in particular about subsampled random convolutions. And in the last part I will also talk about one-bit compressive sensing. So yeah, I guess many of you are familiar with compressive sensing, but let me nevertheless give a brief introduction in order to set up notation. So the problem is to recover a vector x from undetermined linear measurements, so y equals ax, where A is an m by n matrix which has far fewer rows than columns, so it's an underdetermined system. And in general it's, well, not clear how to recover x in this situation, but the key finding of compressive sensing is that recovery is possible if x belongs to certain sets of low complexity, and the standard compressive sensing is sparsity, but I mean there have been extensions to low rank matrices, so so that's also a set of low complexity and further things, but I will now concentrate on the standard sparsity case. So we call a vector S sparse if at most S coefficients are non-zero, and while in practice you usually don't meet exactly sparse vectors, but vectors that are at least approximately sparse. And in order to quantify the error, we introduce this notion of best S-term approximation error, which is the error in LQ that you make by replacing x by the best possible S-sparse vector, and we call x compressible if that quantity decays quickly in S or small or in some sense. Okay, and okay, so how do we recover? So the naive way of approaching this is to look for the vector which has shorted support and is consistent with the measurements. So this is the L0 minimization problem. Unfortunately, this is NP hard in general, and so people have looked for alternatives, and the most prominent one is probably L1 minimization. It's also the best understood one, I would say. So we minimize the L1 norm subject to this linear constraint, and yeah, so hopefully we recover back an S-sparse vector, and theory by now is, well, tells you conditions under which this is possible, and I will come to that. So this is now a convex optimization problem, and there are efficient ways of solving this. So I will not go into this direction. I just mentioned that there are also other alternatives like matching pursuits or iterative hard-thresholding, iteratively reweighted least squares, and other methods. But well, at least many of the results I will tell you for L1 minimization will also apply to these algorithms. Okay, so what's a typical result? So so a standard result here is that if we take well, a generic matrix, so we take a matrix at random, let's say a Gaussian random matrix, then we can, with high probability, recover any S-sparse vector from y equals ax using L1 minimization, provided that the number of measurements scales linear in the sparsity, and well, there's an additional logarithmic factor, and the constant here is absolute, and in fact for Gaussian you can show that in this, well, depends a bit on the type of recovery result, but in practice it's 2, and this can even be shown. So the constants are small. Okay, and I mean, we cannot only recover exactly sparse vectors, but also compressible vectors, and we can also do this if there is noise on the measurement. So everything is stable. And well, you may ask whether this bound here is optimal. Certainly, you cannot hope to recover from less than S measurements, because the crucial point is that in practice you don't know the support of the vector. So we do not prescribe which coefficients are non-zero. But even if you would know the support in advance, you still would need S pieces of information to recover the non-zero coefficients. So, so in some sense, the log factor is what you pay by not knowing in advance the support. And it turns out that you cannot go with fewer measurements, at least if you want stability. So this follows from lower bounds on Gelfand widths for L1 balls, which go back to well, old results. Also, Boris Kashin was involved here. See? Yeah. And okay, so how do you show this? Well, so in the end, what you usually do is derive some properties of the matrix that you need in order to ensure recovery, and then you would like to show for a certain construction of matrix or random draw that these property is satisfied. And we already heard in the talk of Simon that, well, ideally you would like to have a deterministic construction of a matrix, but it's quite hard to actually show these properties for a deterministic construction, and so the best is not this scaling, but basically S squared or S to the 2 minus epsilon. And so let me go into these properties now. So the null space property is actually a characterization of exact recovery, and so it's necessary and sufficient for exact recovery for all S-sparse vectors using L1 minimization. And so what do we require? We look at vectors in the kernel of the matrix and a support set of size S, and now restrict the vector to the support set and take the 1 norm, and then this should be smaller than rho times the 1 norm of the vector restricted to the complement, and rho should be less than 1. So this basically asks that vectors in the kernel are flat, because if you would concentrate the coefficients on a small set and choose that set as S, then this will not be satisfied, and this is somehow natural, because in the extreme case, imagine that V is concentrated fully on such a small set, so it's S sparse. But if it's in the kernel, it's mapped to 0, and then you cannot distinguish the 0 vector and this particular vector using your measurements, and then there is no chance of reconstruction. And so this gives a quantitative version for this, and if the constant is strictly away from 1, then this also implies stability of reconstruction in that sense. So here X is the original vector, X sharp is the reconstruction, and on the right hand side we have the error of best L1, best S-term approximation in L1. And so if X is S sparse, this is 0, and we get exact reconstruction, and otherwise we get a small error if S is approximately sparse. Okay, and you can also make this robust under noise. So so we extend the definition in this way. So this is the so-called L2 robust null space property. So we are asking this inequality for all vectors. Now not only for the vectors on the kernel, because for those the second term would be 0. And if we have this, then also we get stability of reconstruction in terms of adding noise on the measurements. So in this case, we solve this constraint L1 minimization, where we put some constraint on the residual, which is sort of consistent with the with our knowledge on the noise level. And then the error bound also features like a constant times the noise level. Okay, so these are null space properties, and well, you've probably, well, actually this was in the talk by Simon this morning. The restricted isometry property is this chain of inequalities valid for all S-sparse vectors, and if we have that inequality with delta 2s being less than 1 over square root of 2, it actually implies the L2 robust null space property, so we have stability of reconstruction. Okay, and now in order to show this result that I showed you some slides ago on L1 minimization and the Gaussian random matrices as measurement matrices, what you do, you show that for a random draw of such a matrix, you have the RIP satisfied, or you can even show directly that this null space property is satisfied. Okay, so this is nice, but in practice, well, Gaussian random matrices are in most cases not so useful, because if you think of a physical measurement, it's not realistic that you can model this using a Gaussian random matrix. So a Gaussian random matrix is completely unstructured. So usually you have some structure in the matrix that is governed because of some physical laws, or because you have some limitation in how you actually measure. And another thing which is important is that in practice you would like to go to large scale problems, and then you need to work with this matrix, and also in recovery algorithms. And so I mean, there are like some algorithms for L1 minimization which very often multiply with A, or it's adjoint, and if you can speed that up using, say, the FFT, then it's also very beneficial. So we will discuss a particular type of structured random matrices. So why randomness? Well, as I said before, it's very hard to come up with deterministic guarantees in the optimal parameter regime in compressive sensing. So we still would like to have some randomness in there in order to be able to prove something. So here we consider convolutions. So here is the definition of a cyclic convolution. And while starting with a vector of length n, we again get a vector of length n by this. So in order to have something useful for compressive sensing, we subsample the result. So we choose a subset of indices and just observe the result of the convolution on these entries. Let's say we just take the first m entries out of these n possible entries. Okay, and then the task is again to recover a sparse or compressible vector from this subsampled convolution. And as I just said, we also would like to have some randomness in there. So what we do now, we select the generator, this vector b, as a random vector. So for instance, a Gaussian vector or a Rademacher vector, which has just independent plus or minus 1 entries. You can generalize to sub-Gaussian, but if you're not familiar with that, just think of Rademacher or Gaussian. And so the corresponding matrix is a partial random circulant matrix. So well, the circulant matrix generated by a vector b is defined in this way, and then the action of this circulant matrix is simply the convolution of b with x. And if we subsample, that means we just take out rows. And so So for instance, if we take the first m entries, then the corresponding matrix would look like this, and which is basically constant on these diagonals, but the entries along the first row are random. And the good thing is it has a fast matrix multiplication using the FFT, simply using the convolution theory. And by the way, we can extend this also to higher dimensions. So, well, the workshop title is high dimensions. So, well, the only thing I can say in this regard is that you can use arbitrary dimension, and then if, actually things become more effective because in practice, I mean, the relative sparsity, if you go to higher and higher dimension, is well, becoming much smaller. So that things, compressive sensing is probably paying off if you go to dimension 10 or something like that. But okay, I will not go further into this. So where does this appear? One, well, let's say stylized application is a simple radar model. So here we have this station which sends a signal, and then there are some airplanes flying around, and so the signal is backscattered from these airplanes, and since light has finite speed, you get back delayed versions of the sent signals, and the delay corresponds to the distance. And so in the end, this corresponds to a convolution of the distance profile of the scene with the sent signal. And yeah, and this distance profile also, like the magnitude of these coefficients, corresponds to the reflectivity or the size of these objects. And why do you want to do subsampling now? Well, I mean, you usually need to receive here at a very high rate, and if you sometimes you need very expensive hardware if you want to receive at a very high rate. So you can save hardware costs if you subsample. And another application is this one. So compressive coded aperture imaging. So here, okay, so here are two pictures. One is like a very simple pinhole camera. So here you get, so here's the focal plane, and so you get basically on this focal plane the convolution of this real image with the point spread function corresponding to this pinhole. And now what you can do, instead of one hole, you can put many holes, and also put a random pattern of these holes. And then what you observe here is a random convolution of this image with, well, this random point spread function. And now if you would like to do, like, okay, so here at the image plane you have a certain resolution in your CCD chip, but you may want to actually get to a higher resolution, and then you could view these I mean passing to a higher resolution as like observing the image only at the subsampled rate, and then use these schemes to actually go to a higher resolution. Okay, so these are two possible examples. And now the question is, can you actually prove something about this? And so this is a result that took us quite some time to actually prove. But okay, so we were chasing after the restricted isometry property, which I introduced a few slides ago. And so if m again scales linear in S up to these logarithmic factors, then again with high probability the restricted isometry property of this rescaled subsampled random convolution is small. And well, you can combine this now with the result on L1 minimization to get recovery from this number of measurements. So compared with the Gaussian case, you only have more log factors. And in fact, so we needed a new tool to actually get to this result. And so here's a bit of history. So these people showed a bound where m scales quadratic in S, but this you can even achieve with deterministic constructions. And then for some longer while, we together with Joel Tropp and Justin Romberg, we were getting such a result where m scales like S to the 3/2, which, well, we thought was not optimal, but couldn't get something better. And only when Felix Krahmer and Shahar Mendelson joined, we thought about this problem from scratch and got this new bound. So maybe okay. And one thing, so here, so recovery is uniform in the sense that you draw the matrix once at random, and then you get recovery of all S-sparse signals simultaneously. But you may also ask a weaker question. You're given a signal, you draw the matrix at random and ask whether that fixed signal can be recovered with high probability. And in such a scenario, we had an earlier result like that m scales like S log n. But in this case also, well, I mean, stability was not known. I think you can prove it, but get weaker stability T estimates. Okay, so yeah, I'm not sure how much I should go into detail here. Well, maybe a little bit. So maybe so this is the definition of the restricted isometry constants. And so you can also define it in this way as a supremum of this quantity where x ranges over the S-sparse vectors in the unit ball. And now for this partial random circulant matrices, you can write AX, well, it's this subsampled random convolution with psi. And you can also write that as a matrix depending on x applied to psi. So it's also, you switch around the role of x and psi. So it's this matrix is also linear. Well, AX is also linear in psi. And with a short calculation, you see that the expectation of the 2 norm squared of this is actually the 2 norm squared of x. And therefore, we can write delta S as this suprema, where we have this random variable Vx psi and subtract its expectation. So you want in the end a deviation result for this random variable or for this random process where you take the supremum over all S-sparse vectors. And for such type of processes, in the end, we derived a bound. Let me skip this. So I mean, we got a bound in expectation, and here are so-called Talagrand's gamma 2 functionals. So if you haven't seen it, well, I have an explanation on the slide before, but I guess if you see it the first time, that will not really help you. But okay, so that was is the bound in expectation, and also we got a bound in probability, which basically gives the tail above the expectation. And in the end, we use this to get the bound. I told you maybe some remark. So why this is an improvement over previous results. So before we had actually used a tool derived by Michel Talagrand for general so-called chaos processes. So so in the case of a Rademacher vector, we can rewrite this quantity as such a double sum where you omit the diagonal. And And so this is a so-called second order chaos. And now Talleyrand has this general estimate for where, I mean, instead of B star B, you have just a matrix D, and you take the sup over a set of matrices. So you have a gamma 2 functional and a gamma 1 functional. And so before we use this tool, and just, I mean, this always resulted in the strange exponent 3/2. But it also was known that, I mean, this is not optimal in all the cases. And so in the end, for the case that we are in this situation of having positive semi-definite matrices, we basically got rid of this gamma 1 functional, which always caused these problems. So that's how we got there. Okay. Yeah, let me skip this. Yeah, one can use this tool also for other type of matrices and other type of results. But let me pass on now. Yeah, some while ago we thought again about this problem together with Shahar Mendelson and Rachel Ward this time. Whether, I mean, one can reduce the number of logarithmic factors if one also does constructs the set where we subsample also at random. So now there are two sources of randomness. We convolve with a random vector and we subsample at random. And okay, so we use independent selectors. So we take an we sample on a certain index with a probability delta equals m divided by n, and and we do not sample with the probability 1 minus delta, and then in expectation we basically get again m sample values, and well, each realization, well, I mean, the number concentrates around the expectation. And so again, we have now a randomly subsampled random convolution. And in this case, we got a slight improvement. And the interesting thing is that for small sparsity, so less than square root of n divided by log n, we get the same bound as the one for Gaussian randomness, random matrices. So now a structured random matrix for which you get recovery with m equals s log en over s samples. And if the sparsity is a bit higher, then again we get more logarithmic factors, but usually you're interested in small sparsity anyway. Okay, and the way we prove this is actually by going directly to the L2 robust null space property, not passing through the RIP. Okay, and maybe give a bit of comments how we get there. So again, this is the L2 robust null space property, and in the end, how we get there is that this version of the null space property follows from the lower RIP bound for C as sparse vectors, where, well, C is some constant, say 3 or 4 or something like that. So you need to increase the sparsity by a constant, but then you only need the upper bound for one sparse vectors, which is obviously easier to prove than for S sparse vectors. And so let's look at the lower bound. So in the end, we do random subsampling. So if psi is this convolution, then basically the 2 norm squared is this quantity here, where the delta j's are like these random selectors. And now the question is, can we prove a bound, a lower bound that is proportional to the 2 norm of x squared? And in fact, for general psi, this is not possible, because if you take such a vector, which is 1 and then just zeros, then if you do random subsampling, then you will usually result in the 0 vector, because it's very unlikely that you hit this one, and therefore you cannot expect to hold this to hold in general. So you need additional properties of psi in order to prove this. I mean, here's the other extreme, that you just get ones, and then of course random subsampling preserves the L2 norm up to like this factor, which is natural because you've reduced the number of entries. So in the end, we would need to prove that you're more close to this case and not in this case, and so that's basically the strategy. And so what we do, on the one hand we show that this norm is large for all S-sparse vectors, but as I said, this is not sufficient, because it could be that G convolved with X is this unit vector for which you cannot do subsampling or prove lower bounds for subsampling in the end. And so what we also do is that the so-called K norm, so we take the non-increasing rearrangement of this vector and take the 2 norm of the first K coordinates. And if we get an upper bound, which is half of this lower bound here, then the two things together will imply that that if we look at the non-increasing rearrangement of this vector and look at the coordinate theta n, so that this will be large, and then subsampling will result in C1 times theta times m, so a proportional number of m coordinates will be larger than a constant, and this will give you a lower bound. By the way, this will also give you lower bounds in other norms, not just the 2 norm, so in any LP norm, which is also maybe interesting. Okay, so this is the strategy we follow, and for doing this we again use some chaining techniques. Okay, but now let's come to the last part of the talk, so 1-bit compressive sensing. So in practice, if you take measurements, they have to be quantized. So to transform from analog to digital. And here we look at the very extreme case that we quantize just with 1 bit. So in the end, you just retain the sign of the measurement. So you record +1 if the measurement is positive and -1 if it's negative, and well, you somehow need to break the tie, but okay. And yeah, so why is this useful? So again, if you think about a hardware implementation, this just requires a comparator which is very cheap. And also in terms of energy consumption, this is very, very cheap. So if you think of you want to use your mobile phone for a long time without the battery getting down, I mean, this is something that you would prefer. So the first thing one notices here is that the measurements are invariant under rescaling. So if we multiply x with a positive constant, then we get the same measurements. So we can only hope to recover the direction of the vector and not the norm, but in most cases this is fine. Think of an image, whether it's, I mean, if it's getting a bit darker or brighter, this doesn't matter, you would still recognize what's on an image. So so this is usually fine. And so what do you do geometrically here? Well, if you look at one measurement, actually whether you get +1 or -1 specifies the side of the hyperplane orthogonal to the row vector Aj on which the signal x lies. So basically, yeah, if well, okay, so if this is the sphere, and then maybe here you have your vector, then this is the, well, hyperplane cutting out some part of the sphere, so you know that you're on this side, and then the next hyperplane does this, so and so on, and so basically this defines your hyperplane tessellation, and in the end, I mean, your measurement will determine one of these cells in the tessellation, and well, the smaller these cells are, the better you can in principle locate where your vector was. But you also see that now you cannot hope for exact recovery anymore because some information is certainly lost. Okay. So now how do you reconstruct? So here there were some great progress by Roman Verschinen and Jan F. Plan, who introduced this recovery procedure as a convex optimization problem. So again, there's L1 minimization, and then you try to be consistent with the measurements. So you require that the signs are the same, and then well, they don't enforce this normalization that x lies on the unit sphere, because well, that was the original approach, but this has the drawback that you get a non-convex optimization problem because the surface of the sphere is non-convex, but you still need some sort of normalization, because if you do not normalize, well, if you leave this out, then okay, the minimizer will be the zero vector, and so they came up with the idea of putting the L1 norm of AZ to 1, and this you can reformulate as a linear program, which is a nice observation. So you can do linear programming to recover. And they also had a first result for Gaussian measurement matrices. So if M scales in this way, then with probability, or with high probability, then the solution to this program well, satisfies this error bound. So the error scales like delta to the 1/5. And then basically you have the similar bound as in the standard compressive sensing. Then later on, well, actually Simon observed that you can also derive these guarantees for quantized compressive sensing using a version of the RIP with the 1 norm in the middle, which was already mentioned this morning by him. Not in this context, but yeah. So we now use the RIP with the 1 norm here, and we require not only for the S-sparse vectors, but for so-called effectively S-sparse vectors. So those vectors where the 1 norm is less than square root of S times the 2 norm. So this inequality is certainly satisfied for sparse vectors, but it applies to a more general set of vectors. And if you have this, then so this RIP1 effective with parameter 9 S and delta, where delta should be less than 1/5, then you can recover any x on the unit sphere with 1 norm less than square root of S. So in particular S-sparse vectors with small error. And yeah, I think that was even before, isn't it? This result, yeah. Billig and Lacey, maybe the same time, or yeah. Well, I mean, okay. I know that 15 is smaller than 16, but sometimes it's not the actual reflects the actual time when things are proven. So yeah, so they showed that standard Gaussian random matrices, a matrix satisfies this property with high probability, provided that M scales like this. So here it's S log En over S. So even like it's not the, here we had the log square. So it's even just one logarithmic factor. Okay. But as I said before, Gaussian random matrices may not be useful for a number of applications. So the question that I asked myself, well, actually quite a long time ago, but it took some while to get the first results, whether you can do this also for structured random matrices, in particular for random convolutions. So we look at again the subsampled random convolutions, but now additionally take the sign of each measurement. And now G is simply a standard Gaussian vector. And to make things a bit simpler, we also do the subsampling randomly, so we select random positions. Okay, again, well, applications are radar and wireless communications. Well, now deep learning is popular, so well, you could view this as one layer of a convolutional neural network, and then actually these things have been taken up by some people in this deep learning community, but I will not go into detail here. Okay, and so finally with this observation of Simon, we had actually one way of attacking this problem of quantized or one-bit compressive sensing with subsampled random convolutions. So we could show this result, actually establishing this RAP1 basically under this condition. Where m again scales like s log en over s, at least for small delta. I think the scaling is not optimal, but at least we got this result. Before going into detail, actually together with Shahar Mendelson, I could recently prove an improved version of this, so I'll rather present that one, although that's not yet published, so it looks a bit complicated, but the important point is that again, if s is small, like square root of n divided by some logs, then again m has to scale in the same way as in the Gaussian case, like s log en over s, at least for small delta, and if delta is a bit larger, then you get more log factors, but yeah, okay. And if s is a bit larger, then actually we also get a bit more log factor, but still get a bound. So in these cases we also have this RAP1 satisfied, and as we heard this morning, this may not also only be useful for quantized compressed sensing, but maybe also in other scenarios. Okay, then since this is not yet published, I will not tell you the proof. No, the proof is a bit longer, but yeah, and in fact it seems that we also get something for deterministic subsampling, but okay, I have to recheck. Okay. Some more comments, namely on dithering. So as I said, or as we discussed, we cannot recover the norm of x if we just observe the signs of ax. But what turns out to be possible, as was observed and worked by Simon and other people, that if you add like thresholds before taking the signs, then it is possible. So I mean, the idea is that basically if you shift by this tau, then these hyperplanes not just go through the origin, but you can basically cover the get a tessellation of the whole plane, and then get this result. So and in order to prove something, you actually choose this tau also randomly, and then you can also recover the norm of x. And in this context, Sjoerd Dirksen with Shahar Mendelson also proved results both for the sub-Gaussian case and for randomly subsampled convolutions. Then there are also results saying that if A satisfies the standard L2 RIP, then you get recovery results for this dithering scheme. And also, if you're not just looking for one-bit compressed sensing, but scalar uniform quantization, then these people also showed some results for Gaussian A, and actually it follows also from basically the result with the one RIP that you can do this also for randomly subsampled circulant matrices. Okay, so that was basically my talk. Thank you for the attention.
Thank you. Questions?
So at the very end, you mentioned the dithering and choosing the thresholds randomly.
Mm-hmm.
So if you consider quasi-random or deterministically chosen thresholds, then with memory you can improve these things, this noise shaping quantized. Is it something that, I mean, Felix obviously would have
yeah, so using sigma delta
or other methods, obviously.
Yeah.
I mean, this particular one bit is of course very practical, right? So it is very fast, and it's universal as well, in the sense that it's independent of any class of signals you can apply regardless. But
well, sparsity is useful, but
so I mean, I'm not criticizing that aspect, but have you considered, or do you have a reason not to consider these more sophisticated schemes of shifting the threshold?
Okay, so well, I can give you like an answer from a mathematical perspective. So, so I'm not so much from this quantization community, and I was interested in like proving these things for also for structured matrices. So it was more like a mathematical interest. What you use in practice, yeah, but I agree that. But I think there is value for both things. Yeah, no, and other people have considered the like the sigma delta stuff before. So I think, isn't there a result where from RIP, standard RIP, you also get results for sigma delta quantization?
Yeah, there are plenty of results in that direction too. I'm just wondering if you had a particular kind of angle in pursuing this.
Yeah, well, I mean, actually, I talked about this together with Janif Plan in 2012 already, but at some in the beginning we didn't have this characterization or this result using the one RIP, and then to analyze this, I mean, you get problems because the measurements are not independent, and then you cannot do some tricks anymore that they do for the Gaussian case, and the sign function is not even Lipschitz, and I mean, you get all sorts of problems, and only when we saw this characterization then or this implication with the one RIP, we thought, okay, this maybe gives a way of attacking the problem.
More questions? We have time for one more question, so that's from me. You clicked away one last sentence about Bernoulli variables.
Ah, okay.
I wonder a little bit, because this doesn't work here, but then you had something for sub-Gaussians on the next slides.
Yeah. So okay. So for Bernoulli, you can show, well. so you can construct these examples where you have like basically two different sparse vectors which give the same measurements after taking the sign, and then it's clear that you cannot recover using those, at least not the very sparse vectors. I mean, then there are some results telling you, well, if you actually take flat vectors which so are not very sparse, then again it's possible. But with this dithering also, the dithering also helps, and that's the reason why they can do this for the sub-Gaussian case. So, but that uses this additional thresholds, and then the Bernoulli matrices are no longer a counterexample. But if you don't have these taus in there, the Bernoulli matrix causes some problems.
More questions? If not, then we thank Holger again. And then it's time